All right. Hello from my side. I am Atif Mahboob. I wrote my PhD thesis on modeling and use of SysML behavior models for achieving dynamic use cases of technical products in different VR systems. This work was supervised by Professor Christian Weber at Technische Universität Ilmenau, and this work was carried from 2016 towards the end of 2020. I was able to then finish my PhD degree. Before going deeper into the talk that I'm going to have today, I will briefly introduce myself. I have done bachelor's in mechatronics and control engineering from Pakistan. And after my bachelor's, I had the chance to work in Pakistani industry for 2 years. After my work at industry, I realized that I had the urge to go further in my academic career, and this motivated me to start a master's at Sabancı University in Istanbul, Turkey. During this master, I had the chance to go on 2 Erasmus exchange semesters. The first one was at University of Maribor in Slovenia, and the second one was at University of Hamburg in Germany. After successfully completing my master's in mechatronics engineering, I had an excellent opportunity to have a PhD position at Technische Universität Ilmenau that helped me to recently complete my PhD degree, and has been today the cause that I'm talking to all of you over this platform. Since the start of this year, 2021, I am re-employed at Technische Universität Ilmenau as postdoctoral researcher. My talk today will mainly include the motivation for this research, the goals of this research, overall approach, modeling and simulation workflow, and reflection about the core points of this work. What I am not going to talk about is all the bits and pieces of the detailed methodology and the deeper details about the implementation idea. The PhD thesis has been published already online, and it is accessible for everyone. So I suppose if it is needed, everyone can have a chance to look inside the topic in greater detail. The motivation for this work, starting with the main motivation, was to use the models that are available in early development stages, and to use these models to achieve product verification use cases. Usually at the early stage of development, these models are not rich with the information. So this is a challenge to deal with these models and transform these models into verification scenarios. Furthermore, while dealing with models inside virtual product development, we know that models have dependencies in between them, and different tools are linked with each other, usually in active simulation. So a tricky part there is to deal with the existing gaps that are present in digital workflow inside virtual product development. Furthermore, the effort usually to produce or to create these product evaluation use case scenarios is high. So one motivation was also to reduce this effort. And last but not least, the whole of the idea of the development of this model or carrying out this research is to support the product designers in the early verification of a product. Having said that, the goals of this work can be summarized with the help of this slide. We see here some example use cases of a product, and usually during the product development stage, it is desired to think or imagine the situations about a product that can appear in its later life stages. For example, how this product is going to behave in certain situations, what kind of interaction it is going to have with the elements of environment or with humans, etc. So the idea here is to collect or gather the information about the situation or context that can appear in later life phase of a product, and bring it inside a so-called user and task-oriented virtual model. And this model particularly consists of three core components: the product itself, an actor, that is a human interacting with the product in one particular life phase, and the environment refers to a life phase specific environment of that product. And this model should be available at this model should be available at product development stage so that it can facilitate product designer in doing early verification of products. The important part here is the use of virtual reality technology, because it allows the visualization of complex relationship within these models or situations that can appear in later life of a product inside immersive setting. And this really brings an add-on advantage. And while doing so, talking about VR, also one goal was here to integrate VR in the current product development process. Also, now in the current practices, we see the preparation of virtual environments is also a challenging task, usually based on extensive programming based solutions, etc. So the idea here was as well to reduce the overall preparation effort for these VR environments. Moving further towards the overall approach, as I just mentioned, the three core components were product, actor, and environment. And these components actually result from the division of overall virtual model into submodels. And the question is why such a division is needed. And the idea is very simple, because we want to merge, reconfigure, recombine these submodels to form different use case scenarios of a product. What is meant by that? This can be visualized with the help of little graphic that I'm about to show. We can, for instance, have a situation where we have two different versions of a product, and we want to verify these two versions against a fixed combination of actor and the environment model. So the upper part of this use case can be reused in both of the use case scenarios. Or we can have another situation where we have one version of the product, but we have two different combinations of actor and environment model. And here it is again possible to use some part of the already created VR content. And this division at the end helped us to bring reusability inside the VR content. Although this looks like very promising, however, this is quite challenging in terms of its implementation. And for the implementation, we focus towards an approach based on the systematic use of SysML models in conjunctions with CAD models and simulation models to achieve a continuous digital workflow. A question can arise at this stage: why SysML models? So the answer for that is for the implementation, an approach was needed with which these submodels can be described independent from each other. Their interactions can be described in a generic way, and these models can later be combined together, and they can interact together inside one use case scenario to achieve one particular simulation. And SysML is capable of providing these facilities. Furthermore, SysML is also a domain-independent language. Further on, inside systems modeling language, we use the concept of inheritance and instantiation. Let's see for the sake of example, we have our complete system called as high-level solution architecture, and we know that this system consists of three subcomponents, and these components can have, or these submodels can have multiple variants. The trick here is to manage these variants in a way that the interfaces throughout all of the variants of these submodels will be consistent, and this was achieved with the help of the concept of inheritance and instantiation. Now here as an example, we can see for each submodel we have two variations or two examples or categories of that, and then we can move on inside SysML to generate one instance. And on the right side, we see now the instance generation dialog box. Here it is possible to choose against each sub component that is involved in the building of this instance, the variant that we want to have inside that final instance. For instance, here we can see for the product model, we can have two of the possibilities, either version 1 or version 2 of the vacuum cleaner. And after choosing on the runtime, sorry, after choosing on the runtime the individual versions for all three of these submodels, it is then possible to generate one instance inside SysML. An advantage of such an instance is the execution of this instance automatically executes all the submodels that are involved inside one active simulation, or inside this instance. They will be executed automatically in parallel. This is very crucial or very critical when we are dealing with simulations that tend to approach towards real-time conditions. And VR simulation is one example of that, where we require fast or the simulations that are reaching towards real-time conditions. So, this is for me quite an important slide. I will try to take a little bit of time here and try to sum up the overall simulation process here. We have three core components involved inside the overall simulation workflow. We have SysML behavior models, we have a physics engine, and we have a presentation medium. We are aware that SysML in its current capability cannot perform physical calculations on geometrical objects. So this gap was filled by coupling a dedicated external physics engine with SysML behavior models. At the core, SysML behavior models were controlling the simulation inside the physics engine. And once one simulation run is complete, always the feedback was collected inside SysML behavior model. Based on the feedback that was received inside SysML, it was decided what has changed now and what information now has to be communicated to the presentation medium. And then the contents inside the presentation medium are updated by the SysML behavior models, and the simulation can be then updated accordingly. Talking about the presentation medium as one particular example, I can talk about the virtual reality here. This was an integral part of my thesis. So VR may have VR software, VR hardware setting. Particularly in my work, I dealt with three different hardware setups here: the Cave VR system, head-mounted display, and smartphone VR. And then there is one VR. There will be one VR interaction device. There will be one VR interaction device. So product designer is having this device in the hand, and he's visualizing the contents of the simulation inside one of the VR software. If we have a look on this complete flow workflow, we can see that the left half of this slide builds what we call behavior descriptions. That means SysML behavior models together with the external physics engine build the behavior description for the VR environment, and the right side refers to the VR environment. And doing or achieving behavior descriptions that work outside of the VR environment, they have a big advantage that they can be reused independent of what kind of VR software you use right now or what kind of VR hardware setup you use right now. And this was exactly proven on conceptual basis as well inside my thesis with the help of one particular example behavior descriptions. Simulation was achieved first inside cave type VR system, then inside a head mounted display, and then inside the smartphone VR system. On the top of that, there was a certain level of scalability inside the results. That means the behavior description start on the cave that is a high-end output device and go as low towards a smartphone-based solution. Also, the results that were obtained here in achieving these different prototypes inside different VR systems, they were put into empirical evaluations, and the studies were conducted with the help of academic researchers and participants from the industry. The results that we obtained or the feedback that was collected at the end of these studies was very encouraging. Having said that, I just move towards the conclusion of my talk. Just would like to quickly summarize the most key points of my work, starting with the division of overall virtual model into sub-models of product, actor, and environment so that reusability can be achieved. On the top of that, behavior modeling methodology was developed inside SysML to describe these submodels individually and to describe the interaction between these submodels. And the knowledge that was gained in the development of these behavior modeling approach was summarized in the form of general purpose implementation guidelines for someone who later intend to describe dynamic evaluation scenarios of a product with the help of SysML behavior models. Furthermore, when we deal with the behavior model inside SysML, quickly one comes in contact with different execution architectures that can be built inside SysML. And we had a number of these architectures to deal with. I would only mention here the three most significant ones. We dealt with sequential execution architecture, parallel execution architecture, and high-level solution architecture. And the knowledge again that was gained in dealing with these different architecture is again reflected inside these guidelines that I have just mentioned. Last but not least, with the help of this methodology, the overall preparation effort for building these dynamic evaluation scenarios could be reduced with the help of reuse and efficient recombination of these models. Furthermore, this method uses the models right from the early development and helps in achieving continuous model workflow, as well as generic information exchange between different tools that are involved inside an active simulation. With the help of reuse of the submodels or with the help of reuse of already created VR content, it is possible to achieve time and cost advantages. The VR hardware that I showed in the last slide as output medium can be replaced with any other technology. For example, can be replaced with a two-dimensional just a display screen. And the physics engine, this last point I see as a very critical point. And as far as I know, this is the state of the art right now as well. The different industries, industrial organizations have domain-specific tools, and they try now to integrate these tools with SysML models. And in order to do that, the idea that's presented inside my work to couple an external physics engine with SysML models can be used on the same line to integrate any domain-specific tool with SysML models. Having said that, I thank you very much for your attention, and I pretty much look forward to your questions.
Atif, thank you very much for your presentation, and also congratulations from my side to you, and greetings to
Thank you very
Ilmenau.
much.
So Atif,
Thank you
unfortunately,
very much.
time is flying. We just have time for one little question, but this is a quite specific one. I'm going to ask it right away to you. How far is the concept applicable today in real-life scenarios of the industry, considering the interoperability challenges in a heterogeneous environment for both SysLM and cat shape representations?
Well, it's a very specific question. I will try to be as precise as I can. So, in my opinion, the method in its current form can be used and directly implemented. And a part of this question referring to the interoperability between CAD and SysML models and etc. This has already been implemented inside this work. So the question for me will be to what level of detail we want to do this at on the way the question is asked. I think it is already doable in its current stage based on the results that are obtained inside my work.
Wonderful. Atif, thank you very much for your time. And again, congratulations from my side.
Thank you very much.